What's up everyone, it's Powell, and in this video we're going to talk about some weird circle cases that happen with arcs and lines. Now in a previous video I talked about central angles and the fact that if you have a central angle, which is an angle in a circle whose vertex is at the center and it intercepts an arc, the measure of the angle is going to be the same as the measure of the arc. So in this case we have angles alpha and beta. They're central angles, and the arcs they intercept are 40 degrees, so they're also 40 degrees. And they're also the same measure because they're vertical angles. So since alpha and beta are vertical, they're also 40. But what happens when two chords intersect? And they don't intersect in the center. So you might notice that one of the arcs for alpha is bigger than the arc for beta. So I know that alpha can't equal 80, and I know beta can't equal 30. And I know that because alpha and beta are vertical angles, so they have to be the same. So the way we find them is we average them. And I'm going to write it in a very specific way because the next example, it gets a little weird. So what I'm going to do to find alpha is I'm going to take the bigger angle, add the smaller angle, and divide by 2. Or I should say bigger arc measure plus small arc and divide by 2. And for this particular example, it's 80 plus 30. So alpha is equal to 80 plus 30 divided by 2, or 110 degrees divided by 2, or 55 degrees. So alpha is equal to 55 degrees, and beta, because they're vertical angles, is also equal to 55 degrees. And I kind of made a weird smiley face with that. So that's if the chords intersect inside. What happens when the angle made by the two lines is outside? Like in this example. So I guess if I extended them, they'd be secant lines. But I have two lines that intercept two arcs in a circle, but they intersect outside. So this is a little different, and this is why I wrote that formula the way I did, because in this case I don't average them. I take the big arc, I subtract the small arc, and divide by 2. So in this case, alpha is equal to big arc minus small arc divided by 2. In this example, it's 100 minus 40 over 2, or 60 over 2, or 30. So alpha is equal to 30 degrees. And that kind of makes sense because if we look at alpha, and granted this isn't drawn to scale, but if we look at alpha, the average of 140 would be 70, and alpha looks a lot smaller than 70. So you can take advantage of the fact that if the diagram is drawn to scale, if you average them, you can kind of see that you might have the formula mixed up. And you could also write this as the absolute value of the difference of the arcs over 2, and that way you don't have to get the order necessarily right. But that's if you have two lines that intersect to make an angle both inside and outside the circle. And there's one other property I want to go over, and it involves inscribed angles. And again, I did a video before on inscribed and central angles, and in this case, we have inscribed angle beta, and an inscribed angle is an angle whose vertex is on the circle and it intercepts an arc. Its two sides go through the circle and intercept an arc. And we know that they're half the measure of the intercepted arc. So I know that beta is 25 degrees. But alpha is a little weird because one of its sides goes through the circle, but the other side doesn't. The other side is actually, I guess, a tangent ray to the circle. But it still is an inscribed angle, and it still is half the intercepted arc. So even though the two sides of the angle don't go through the circle, alpha still is half of 130, or 65 degrees. So those both are inscribed angles, and they're both half their arcs. So these are just a couple of weird things that crop up with intersecting lines and circles and central and inscribed angles that might help you when you're tackling a large circle network. If you like this video, please subscribe and be sure to share it with someone that you think might benefit from it. Thanks for watching.